Welcome friends, welcome to my channel Talking Physics with Piyas Sarkar. Today we shall learn about first law of thermodynamics, but it is not new to all because you already write or know the statement of first law of thermodynamics. So what is the new to be learning in my channel? Now you just recollect or do not understand the first law of thermodynamics and written in the examination copy. Today we shall fully discuss the view and and also understand why this law is written as in the mathematical form del q is equal to del u plus del w, and from when and how it is written from, but and also why it is written. Any mathematical formula cannot be written without any reason. So today we learn the reason of first law of thermodynamics mathematical form, number 1. Number 2 is the statement of first law of thermodynamics, and number 3 is the limitation of first law of thermodynamics. So don't be wait, let's start.
We all know that the first law of thermodynamics, first law of TD, that is thermodynamics, the basic equation is all we know, that del Q is equal to del U plus del W, or in some book this is written as dQ is equal to du plus dW. Now you know that dQ, du and dW is change in that the total heat supplied to the system, du is change in internal energy, and dW is external work. But my question is here that how this equation comes from, but from when this equation comes from, and why we written as that dQ equal to du plus dW. Can anyone answer it? If you know it, very well, but some student who are fair in physics and do not know the basic theory, please view my channel and subscribe my channel. I will tell you from basic to advanced level. So dear students, let us start first law of thermodynamics. Here I can elaborate you just two process. First process and second process. In first process, in a cylinder, a gas is enclosed in a cylinder with a piston, with a frictionless piston. If this is frictionless piston, then the gas is enclosed in a piston, and here the piston is fixed, and the temperature of gas molecule is T1 and the temperature of the wall of the container is T2, then here T2 is greater than T1, that is the temperature of the container wall is greater than the temperature of the molecule. And in the second process, the same figure is drawing, but here the temperature of the wall is T1 Kelvin and the molecule is also T1 Kelvin, but the piston is moving inside. This is movable piston. Here the piston is movable, here the piston is fixed. In both cases, the gas will acquire some energy. As heat is a, what is heat? Heat is a form of energy. So this energy can be transferred to a system in two ways: by supplying heat from outside or by doing some external work. So in first case, as the temperature of the wall of the container is greater than the molecule temperature, therefore the molecule strike with the wall molecule, strike with the molecule of the wall, we know that and get some kinetic energy. But here the kinetic energy of the wall molecule is greater than the kinetic energy of gas molecule. So, when the kinetic energy of wall molecule is greater than the kinetic energy of the gas molecule, some of the kinetic energy of wall molecule is transferred to gas molecule, and the additional kinetic energy which acquired by the gas molecule is shared between the all gas molecule, This increase the kinetic energy of all molecule, and we know that the kinetic energy is directly proportional to the temperature, in Kelvin scale. So, here the internal energy of the molecule is, as internal energy is also a function of temperature, so internal energy is increased. Here internal energy is increased. So, here the piston is fixed, and due to variation of temperature between the molecule of the gas container and the wall of the molecule, and the molecule in the wall of the container, the internal energy increase. Internal energy increase here by applying heat from outside. Internal energy is increased by applying heat from outside, and here the heat, that is delta Q, is taken as positive. Delta Q is taken as positive. In the second process, the temperature is not given from outside, but the piston is moved along this direction, that is inside position, with a velocity u. Now we know the gas molecule is randomly collide with each other, and they go with velocity v1 and collide with the piston and rebound back with velocity v2. Then their velocity is increased by the law of elastic collision. If we consider it that the collision between the molecule and the piston is elastic, then v2 equal to v1 plus twice into speed of the piston, that is v2 is equal to v1 plus 2u. Here the gas is also allowed to expand, because here as the piston is movable inside and it tries to compress the gas, then the work is done on the gas. Here work is done on the gas. Therefore, again, as work is done on the gas, its internal energy will also increase. Then again, its internal energy also increase. But here it loses some kinetic energy. Here internal energy is also increased. That is, in two cases the internal energy is increased, in which the internal energy is increased by applying heat, or here by work done on the gas. Therefore, in two cases the internal energy will increase. Now, as In practical case, these two processes will simultaneously occur. These two processes occur simultaneously. That is, in practical case, the piston is moved inside and the gas is heated from outside. The two processes will simultaneously occur in practical case. As is heated from outside, it expands. That is, it expands and the piston comes from this position to outside position. Because of, as we heated from outside, the gas molecule gains energy and work is done by the gas molecule, not work is done on the gas molecule. Work is done by the gas. Here work is done by the gas. Work is done by the gas. Now, as work is done by the gas is taken as negative. Now, work is done by the gas is taken as negative, that is delta W is negative, and as heat is supplied, here is taken as positive, that is positive delta Q. So, heat is supplied from outside is taken as positive and work is done by the gas due to its expansion, that is the work is negative. So, what is the energy difference? Energy difference is equal to delta Q minus delta W. Now, this energy difference will cause two effects. First is the gas molecule along with container is moving, or the internal energy is increases. The gas molecule with the container is moving or the internal energy increases. But the gas molecule with the container with moving in such case when the system moves systematically, that is in a organized way, but all times it is never possible. So, if we neglect the first phenomena, then we can get that only this change of energy increases the internal energy of the gas molecule. So, we can write that the change in internal energy is given by delta U equal to the difference in energy due to heat and external work done. Therefore, we can get the total heat delta Q equal to change in internal energy plus external work. This is nothing but the mathematical forms of first law in thermodynamics. I hope you understand it. So, again we can write it as when a system is taken some heat, is capable of doing some work, is equal to the sum of change in internal energy plus external work, that is del Q is equal to del U plus delta W is the first mathematical form of first law of thermodynamics. Now, this delta Q for monoatomic gas, this is change in delta Q is for translation and only for translational motion. The internal energy is due to only the translational motion. For monoatomic gas, that is delta U is only for translational motion. But in ideal case, for ideal gas, it is the sum of translational plus rotational plus vibrational motion. These three types is the form of kinetic energy plus attractive force between the molecule, which is nothing but potential energy. That is the sum of kinetic energy plus potential energy is equal to internal energy of a gas molecule. Now, if a system goes from initial state I to final state F, the value of delta Q minus delta W remains same. That is if a gas goes from initial to final state via several processes, that is if it gets from initial to final point, then here through several processes, then point 1, 2, 3, let us say here the value of delta Q is changed and the corresponding delta W is also be changed, but the difference between the delta Q and delta W do not change. It is always same because internal energy does not depend on the path, it is only depend on initial and final point. It does not depend in the path in which the process occur, it is only depend on the initial and final point. This is the basic point of internal energy. Now, if we summarize the whole matter, you can get that when a gas is heated from outside, the heat is taken as positive when heat is taken by gas. Please, every video of my channel you will see to the last minute, because very necessary information which I give in between the video will be missed out if you skip this. Please don't skip. Now, heat equal to negative when heat is drawn from the gas. Number 3, work is done by gas is equal to positive. Number 4, work is done on gas is taken as negative. Work is done by the gas is taken as positive and work is done is negative. Now, if the heat is positive and heat is positive, then the internal energy will be increased, and if work done is negative, the internal energy will be also increased. So, we know the first law of thermodynamics, how it comes from. Now, we can show the limitation of first law of thermodynamics. Number 1, it cannot tells about direction of heat flows. Number 2, it cannot tells the situation in which heat is converted into work. I can explain the point. First I can write it. It cannot tells the extent or limit by to which extent to which heat is transferred to work. This is the basic limitations of first law of thermodynamics. It cannot tells, only first law of thermodynamics tells that heat can be transferred from hot body to cold body, but it cannot says why heat cannot flow from cold body to hot body. So it cannot tells about the direction of heat flows. It cannot tell the situation in which heat is converted into work. When the speed of a car is very fast, then the kinetic energy is converted into heat, and when it is sufficiently heated, it can be stopped. But the first law of thermodynamics does not say that why the heat produced is not again converted into work and it put back to its motion again. And the third law, it cannot change the external limit, that is why a Carnot engine or a heat engine, I can say it in the later video what is heat engine, Carnot engine. Why a Carnot engine? A Carnot engine is basically a engine which transfer heat from a hot body and doing some external work and reject some amount of heat. If Q1 heat is taken from the hot body and it doing external work W and rejected the balance heat into some cold body, that is the Q2 is rejected to it. It cannot tells how, it cannot tells the why heat engine cannot, the heat is cannot 100% converted into work. That is why it can reject an amount of heat to the sink. This is called source and the lower temperature body is called sink. That is, it cannot tell what percentage of heat or why the 100% of heat is converted into work, because it is not possible. If this is possible, then the efficiency of the engine will be 100%, which is practically not possible. So these three are the basic limitations. You can write in your copy basic three equations. So in this lecture we can know that the basic law of thermodynamics, del Q equal to del Q equal to del U plus del W is where it comes from, what is the basic formula of thermodynamics, what is its statement, and the limitation of the first law of thermodynamics. If you like my channel, please subscribe for better future better video. Thank you.